advantages and disadvantages of threaded joints. After that, we discussed about the different types of threaded joints. Then we discussed about what is a bolt of uniform strength, and after that we discussed about some of the terminology what we are going to use in these threaded joints. So I think in that terminology, few more slides are left. So first we'll go through those slides, and then I'll show you how to use the data book and how we can using the data book, how we can solve the problems. So corresponding to the given problem, how we can choose the formula for the data book, and then later we'll take up actual problems and we'll try to discuss those things also. Okay, I think last time we discussed up to this point, that is tensile stress area. This is over, I think. So we discussed up to this point. This tensile stress area is nothing but the testing threads of rods, that an unthreaded rod having a diameter equal to the mean of the pitch diameter and minor diameter, that is dP plus dC by 2, has the same tensile strength as the threaded rod. So therefore, if you take the diameter equal to dP plus dC by 2, or average of pitch diameter and core diameter, then if you calculate the area based on the diameter, then we'll call that area as a tensile stress area. Why you call this one as a tensile stress area is whatever may be the cross-sectional area you got from dP plus dC by 2 taking as a diameter of the bolt. So then whatever stress you calculated, that if you take that bolt and if you load the bolt with the same load and if you measure the stress in that one, it is same. That means, so here we have taken this dP plus dC by 2 as nothing but a unthreaded bolt of same length. So therefore, this, if there is no thread, if you take a bolt, I cannot call it as a bolt, simply I can call it as a rod. So which have no threads. So that's why it is called unthreaded rod. If you take a unthreaded rod and if you apply a tensile load to that, then whatever may be the stress induced in this is same as the stress induced in the bolt having this diameter. dP is the pitch circle diameter and dC is the pitch circle diameter. So if those are the diameters of your bolt, then if you take dP plus dC by 2, you will get a diameter. If you take the diameter as this unthreaded rod, so then if you load this unthreaded rod with this diameter, whatever stress induced in this unthreaded rod is same as the stress in the bolt. So that's why we call it as a tensile stress area. So here in the diagram you can clearly see you have different diameters. Even though you have a different diameter, that is major diameter, minor diameter, pitch circle diameter, like this. Suppose if this bolt or thread is subjected to some tensile load, so now I want to calculate, let us say it is subjected to some axial force P. So I want to calculate what is the stress in this bolt. So we know stress for due to axial load, the formula is P by A. Stress is nothing but P by A, where P is the applied load. Here we are applying a load of P newtons. Newtons or kilonewtons, whatever it may be the load, the P is expressed either in newtons or kilometers. So we know the P. So now to compute this sigma, that is the normal stress in the bolt because of this applied load P, I should know A also. So that is A is nothing but cross-sectional area of the bolt. So now if I take a section at some particular location, something like this. So now here I have different diameters. That is I have a minor diameter DC or root diameter, similarly major diameter and pitch circle diameter. So now which diameter I need to consider to calculate this area? That is the next question. Because you have three different diameters, which diameter you have to consider for calculating area? So to answer that question here, you have to consider the diameter, none of these three. You have to consider either major diameter or pitch diameter or minor diameter. So we are not going to consider any one of these three, even though in the terminology you learn about this major diameter, pitch diameter or circle circle diameter and minor diameter. But to calculating the tensile stress in the bolt, we won't use these three diameters. We'll use a diameter which is equal to this one, dP plus dC by 2. So then you know the dP, you know the dC. So take the average of these two diameters. Then the diameter is used to calculate this area. So then this area is called this tensile stress area. So because we are using this area to compute the tensile stress, so this area A is called the tensile stress area. This is important because you have different diameters. You may have to have a doubt how which diameter we need to consider while computing this. So then to avoid that confusion here, you have to use this is the diameter dB plus dC by 2. So now again, so for every, because we will use different number or so many number of bolts and nuts in a given assembly, and also we have a different sizes are there. So now calculating this diameter for each and every bolt is going to be a difficult task. So then what we are doing is people have standardized that and they already calculated what is the tensile stress area for each bolt. So based on this capital D. So that means generally we'll designate bolt by nominal diameter. We'll designate any bolt by its nominal diameter or major diameter, if it is capital D for internal threads and small d for the external threads. So now once you know the capital D or small d, that is the nominal diameter for internal as well as external thread. So if it is internal thread, you need to look at it to capital D. If it is an external thread, you need to look at it to the small d value. Once you have a d value in the data book, you need to pick d value. So based on that, in the data book, they will provide this area directly. So instead of calculating dP plus dC by 2 and from the diameter calculating the tensile stress area, in the data book, so of course, though in the whatever values are there in the data book, they are calculated based on this diameter only. So, but instead of calculating every time, what we can do is we can. Hello. నానా నేను మళ్ళీ ఫోన్ చేస్తా, క్లాస్లో ఉన్నా, తర్వాత ఫోన్ చేస్తాను నేను 10 నిమిషాల తర్వాత, 6 గంటల తర్వాత. So instead of calculating every time, so the standard is, because it is a standard one, so it is provided in the data book itself. I'll show you where you can see that how you can pick the tensile stress area for a given nominal diameter. Where if it is a bolt, you have to do small d. If it is a nut, you have to take capital D. Okay. So that's what we already discussed here. This area is used for purpose of calculating the tensile strength of the bolts. Tensile strength in the sense, what is the maximum allowable stress in the bolt? So that we'll call it as a tensile strength. So if you know the maximum allowable strength, again that is based on only P by A. So this if for a given bolt of diameter D, A is fixed. So then I can calculate what is the maximum load carrying capacity of that bolt also. That we'll call it as a tensile strength. So now after that, I think we have some ISO metric threads. So these are the threads generally used in most of the applications. We know in case of a metric threads, the angle is included angle 2 alpha. So here you can see that, clearly see that the included angle is, or threaded angle is 60 degrees. So this diagram will show you both the internal as well as external thread diameters. So internal thread diameters are used denoted by the capital letters D, dP and dC, and external thread diameters are represented by small letters. So this is the standard everywhere. People will follow only this notation. So this is a V thread. He has shown both internal as well as external threads and a single diagram. So I think you already familiar with this because you already done in our CMDP course for this. So generally these are widely used. Fastening threads are usually V threads. So that means you can see that the shape of the thread profile is V. So you have other profiles also there. So that is acme threads are there, like spare threads are there. So depending upon the application, the type of thread profile will vary. Here we are discussing about the fastening. That means we are discussing about the creating a bolted joints. So in case of bolted joints, the preferred threads are V threads. Whereas suppose if you want to use thread in a power transmission, so for power transmission, we go for either Acme threads, or you can go for spare threads where friction is less. See, if you want to transmit the power, you should have loss is minimum. So that means there should be minimum loss of power. So therefore, we'll choose thread which is having a very less friction. If friction is more, there is a more energy is lost in the friction. So we'll choose threads such that the friction is less in case of power transmission. So the threads which are having less friction are examples for that is Acme thread and spare threads. Whereas in case of in our application, this particular application, that is bolted joints, we require maximum friction so that the joint is tight. So to have a maximum friction, so in case of V threads, the friction is going to be maximum. So that is the main reason why these V threads are extensively used in the applications of these threaded joint or fastening threads. So they offer the following. So like L thread, V threads results in higher friction, which lessen the possibility of loosening. And also here, I think in our engineering mechanics, I don't know whether you studied about that point or not. So there is a thing called self-locking. So self-locking means if you take the thread angle and friction angle, if the based on the relation between the thread angle and friction angle, we can specify the screw as a self-locking thread or not self-locking thread. Especially in power transmission, you require self-locking threads. Whereas in case of this screw fastening, we don't bother about whether it is a self-locking or not. So only in case of power transmission, we'll concentrate whether the thread is, or we'll take the advantage whether the thread is a self-locking one or not. Okay, here we are not bothered about that point. So V threads results in higher friction, which lessen the possibility of loosening. So if you remember, while discussing about the advantages and disadvantages of these threaded joints, so one of the disadvantages what we discussed there is these threads will loosen easily when they are subjected to vibrations. So that is one of the disadvantages of these threaded joints what we discussed during the while discussing about these advantages and disadvantages of these threaded joints. The reason for that why they are loosening is because of vibration, the frictional force is going to be reduced between the two connecting parts, so which will result in loosening of the threads. So now, if you provide a thread which is having a higher friction, then the possibility of loosening is less, or the chances of loosening of the connection is going to be less. So that's why in case of V threads, since they are providing higher friction, they are used in this screw fastening, or maybe the in connections. Then the next advantage is V threads have higher strength due to increased thread thickness at the core diameter. So this is another advantage. So based on these two advantages, so most of the bolted connections are followed or uses V threads only. So that means whenever in somewhere in maybe in the next some problems, if you think about while considering the threads for that, so if they ask or if they specify what is the profile of the threads, so then simply you have to take it as a V thread only. So don't choose some other thread. So maybe in some examples, sometimes if there is some data is missing in some problem, suppose if you want to solve the problem, you require a thread angle. So then in the problem data, they are not given the threaded angle. So that is alpha is not given. So then, so you cannot simply say that the data is missing, I cannot solve this problem, because you are provided with the data book. So using data book, you can identify those values also. But to pick the data threaded value or that alpha value, what you should know is for a given application, what type of thread is going to be used. That is, if it is a power transmission, what type of threads you are using. For bolted connections, what type of threads they are going to use. So based on that, you need to pick the value from the data book and you need to solve the problem. So Simply we cannot escape saying that the data is insufficient, the problem cannot be solved. So sometimes what they can do, what they can do is, so they'll give the problem only the requirement they'll give. They won't give you the another additional data. So let's say I want you may ask something like this: design a bolted joint which is capable of carrying a load of some 30 newtons, 30 kilonewtons. Simply within one sentence they may give the question. So then, so you cannot say that with only the load I cannot design the joint. So you have to make use of the data book, and you need to collect the information which is required for the entire problem from the data book, and then only, and next you need to solve the problem. But you cannot escape that saying that the data is not given insufficient. Because why we are not able to claim that? Because data book is available to you, so you can pick the data from data book, and all the entire information is available in the data book. The information is not there, then we can say that we are insufficient, we have insufficient data. But since the data book is providing to you, you cannot say that the data is insufficient for the given problem. By mistake, sometimes what happens is, by mistake the data may be missing, or sometimes people are intentionally they are not giving the data also. So because they want to test you whether you are able to use the data book or not, or whether you are you should know the things or fundamentals behind designing of the particular joint. So to test that, they won't give you the all the data. So intentionally they will miss the data. So they will skip the data and they will give you only the requirement. So then you have to completely refer the data book, and you need to collect the complete data regarding to that particular problem, and then only you need to solve the problem. So that is one more important point you need to remember. Not only in case of this bolted joints, so in all other things also, whatever we discussed earlier also, and all our topics, since the data book is available to you, you need not get all the data in the problem itself. So sometimes there may be a chance of you need to pick the data from the data book by collecting entire information. So that's why I'm again telling you, so the importance of the data book, and how to, just buying the data book is also not enough. So you should know where it is, what data is available, where it is available, and how I can collect the data. That is also important point. So for that, at least you need to go through the data book, all the pages. After buying the data book, you need to go through all the pages corresponding to your syllabus. So whatever syllabus is there in that, you need to go through all those things in the data book. If you do that, what happens is, you should know, you will know, or you will are familiar with all the available data also. Sometimes if you remember or forgotten some formula also, then you may have a chance of easily picking up that formula from the data book. If you know this data, and this data is available in the data book. So if you know that, no need to remember the formulas also. Simply you will open the data book and you will pick the formula from the data book, and you will apply that formula to the given problem, and you can easily solve the problem. That is one advantage here. The same thing will also become disadvantage, because you are not at all interested in buying the data book and not at all looking into the data book. So that is going to be a big disadvantage for you. If you are sincerely following the data book, then that is going to be advantages for you. So no need to remember all those formulas or all those concepts also, or some other things also. Sometimes what they give is in 2 marks, they may give draw a thread profile, something like that. They may give the question also. So then in that case, what you can do is simply you can open the data book. In the data book, all the thread profiles are available. So then from that you can easily answer that question, and you will get the marks for that question also. So, but you should know whether the thread profile is available in the data book or not. Then only you can do that. Otherwise, it is not possible to answer that particular question, because you are not preparing that thread profiles also. Because here majorly we will concentrate on how to design the threaded joints and how we can do the analysis. But we won't discuss all the thread profiles, what is the angles, all these things. So by chance you may have a question in the examination, then you can use the data book and you can answer it. So that's why data book is a important thing for you. Okay, right. So in case of V threads, since the friction is very high, they are most preferred thread profiles for fastening. And also the other advantage is they have a higher tensile strength due to increased thickness at the core diameter. And wheel threads are more convenient to manufacture. This is also another advantage. So if you compare to the other threads, these are the easiest way or easiest form of the thread which can easily manufacture. Okay, so then next again, so we are discussing about this metric screw threads. In that, the profile of the thread is V shape, and again in that, the metric threads are divided into two categories based on pitch value. So here they are called as coarse and fine series. What is coarse series? What is fine series? So we know every thread profile will have a pitch that we already discussed. I think if you go to that terminologies here, you can see here we define a pitch of a thread for both internal as well as external threads. So whether it is an internal thread or external thread, it doesn't matter, it will have some pitch. Pitch is nothing but the distance, the axial distance between two successive roots or two successive creds. We'll call it as a pitch value. So now based on this pitch, for the same given diameter, so let us say for a same given major diameter D, if this pitch is not same, let us say I have taken a 12 mm bolt. So 12 mm bolt means a nominal diameter of the bolt is 12 mm. So for that you have a different pitch values also there. You cannot say that there will be only one pitch. If I choose 12 mm bolt diameter, always the pitch is same. So we cannot think like that because there are different pitches for a 12 mm bolt diameter also. So then, because depending upon the pitch, they divided into two types of series. They are called fine series as well as coarse series. If number of threads for a pitch is more, then we'll call it as a fine series. If they are less, we'll call it as a coarse series. What is the definition here? In case of coarse series, number of threads per pitch, they are less. Whereas in case of fine series, number of threads per pitch length, they are more. That is one way of defining a thread, whether it is comes under coarse series or fine series. So, but the thread profiles are same. See, that's what written here. Metric threads are divided into coarse and fine series. The thread profiles in these two cases are generally similar. The coarse thread is considered as basic series. So generally, the coarse series are considered as a basic series. Coarse threads are why they are considered basic series? Because of these following advantages. The static load carrying capacity of coarse threads is higher. So that's why if you don't have any restriction, what is the pitch you need to use for the threads? So people will select the coarse threads because they have higher load carrying capacity. The static load carrying capacity of coarse threads is higher. So if there is no restriction on what is the pitch of the thread you need to use, then definitely people will go for coarse threads because they are providing higher static load carrying capacity. Then the second one is, so coarse threads are easier to cut. Why they are easier to cut? So now, like I already told, coarse thread means number of threads for a pitch length. Suppose if this is my pitch length, if I want to cut 2 threads for a pitch length, something like this, here and here. So it is easy when compared to if I want to cut 10 threads here in the same length for the same pitch length. If I want to cut 10 threads, something like this. So 10 threads, it is somewhat difficult or complicated when compared to cut only 2 threads within the given length. So therefore, these coarse threads are easier to cut than fine threads. Then last one is the errors in manufacturing and where the errors in manufacturing and wear have less effect on the strength of the coarse thread than that of fine threads. Why? Like I already said here, in case of coarse thread, the number of threads for a given length is less. So because there are less number of threads, the wear is also less. So that's why and also errors are less. Why errors are less? Since you are cutting only 2 threads. So for a given length, if the length is small, in the small length, if I want to cut 10 threads with accuracy, then it is going to be a difficult thing. So that means you have an error in this. If I go for only one thread in this one, I can easily cut that thread. So therefore, the errors are also less in case of this coarse threads. So these are the advantages of this coarse threads. Then coarse threads are less likely to seize during tightening. So means what it is, seizing of the thread is nothing but just it will stuck into the connection. So that means it cannot be rotated further in either direction. So while tightening it, so we need to apply some torque to the bolt, so through bolt head. So after tightening some part of tightening, then what happens is they may cheese. So some bolts, but if the pitch is too fine, then the thing is going to be happen. Whereas in case of this coarse threads, the problem is not there. So then that is going to be the another advantage. So coarse threads have more even stress distribution. This is also another advantage. So now based on this, so that's why they are called it as a basic series. And while selecting a thread, so if pitch is not the criteria for the selection of the thread, then definitely we straight away the selection is based on this basic series. You need to select the basic series. How you can know this is the basic series or maybe a derived series or a fine series? I will tell you. I will show you in the data book what is the basic series, then what is the fine series. So while showing the data book, I'll tell you those things. Then other type of thread is fine series. So fine threads, there are also some advantages when compared to the coarse threads. So that is, fine threads have greater strength when subjected to fluctuating loads. So here, it's again the same thing. This point comes from that these bolted joints will loosen when they are subjected to vibrations. Vibration is nothing but some kind of fluctuating load. So vibration means to and fro motion. That means the motion will be something like this. Here, a fluctuating load is also something like this. The load is something like this. So it is, we'll call it as a fluctuating load or fatigue load. So when threads are subjected to fatigue loads or fluctuating loads, we have seen that the bolted connections are loosened very quickly. So that is the disadvantage. So now if you go for fine thread, that means if you go for more number of threads for a given pitch length, then that problem may be overcome by certain amounts. So therefore, this is one of the advantages for these fine series threads. So they have greater strength when subjected to fluctuating loads. Fine threads have greater resistance to unscrewing as a result of low helix angle. So this is also, we already said here, unscrewing. Unscrewing means loosening of the nut, loosening of the joint. Hello? So fine threads have a greater resistance to unscrewing as a result of low helix angle. Why you have a low helix angle in case of fine threads? For a given length, you are cutting a more threads means your helix angle is going to be less. So that's why it have more frictional resistance. So it have a greater resistance. That is nothing but the frictional resistance for unscrewing. Then therefore, threads with fine pitch are more dependable than threads with coarse pitch irrespective of self unscrewing. So like we already talked about the self locking. So here, if you want to use that particular purpose, in the connection have a self, in order to avoid self unscrewing. So then you need to go for these fine series threads. Okay, so now here I have shown two pictures to you. Anyway, I'll show them on the data book also. So here you can see that these are the screw threads having coarse series. Here the heading is coarse series. Here you can see M4, M5, M6, M8. So he said it is a designation. Why it is generally all the metric bolts having metric screw threads are denoted by a letter capital M. Capital M is for metric screw threads. So that is the designation people will follow. So then M followed by you have what you have after that. See, M followed by 4 is there. So what it means? 4 means here this is the nominal diameter. M4 indicates that a metric thread having a nominal diameter of 4 mm. So that's what you can see it here. Next column you have a nominal diameter or major diameter. So in that he has expressed that as mm. So you can see that here 4 is there. So then you have a pitch value here 0.7 mm, and then pitch diameter. He has given pitch diameter, core diameter, and he has given the tensile stress area also here. See, you can see, suppose this M4 bolt is subjected to some tensile load, let us say 10 kilonewtons. So if we ask you calculate what is the stress in the bolt, simply what you have to do is you need to take the load which is given 10 kilonewtons divided by this tensile area. He has given this is, remember it is always in mm square only. So whatever provided in the data book, that is in mm square only. So you need to take the data 8.78 as mm square and you substitute it and you write the solution. So similarly you can look at into the other things also in the column. Next you have M5. M5 means M stands for metric thread, 5 stands for its nominal diameter. M5 means a bolt or nut, whatever it may be, bolt or nut having a metric thread of major diameter is 5 mm. So that is the designation M5. Similarly M6, M8, M10, like that you have different diameters. So I have taken only the portion of that image from that table. So you have up to higher numbers also. So here M12 means major diameter 12 mm only. So here in this column you have its corresponding tensile stress area also. You have a tensile stress area also here. Straight away from the data book you can pick that and you can find the tensile stress in this area also. Then in the second picture you can see that this is for fine series. So here see the designation is also different here. Designation, you look at this column, designation column here. This and this you compare. Here you have only M4, or if you take M6 you have only M6, but here you have M6 by cross or by, we'll call this one as a by, will designate as 1 by 1 means what it is. So here this designation, if you have a designation something like this, M6 by 1 means it is a fine series. If simply you have only M6, this part is not there, then we can call it as a coarse series. Only you have M4, M5, that means letter M followed by the nominal diameter. If that is only there in the designation, we will call that one as a coarse series. But not only that, only M4 or M6 followed by some other number crossed by 1. So this one indicates the pitch value. One indicates the pitch value, then I can say it is a fine series. So now here you can see that M6 cross 1 indicates that M is a major diameter, M for metric thread, 6 for major diameter having 6 mm. Then cross 1 means 1 mm is going to be the pitch. You can see that here 6 and 1 is also there here. So in the next row, if you look at in the next row here, you can see that next row is also M6 only. M6 cross 0.75. So that means here for same M6 bolt you have two different types of pitches there. One is 1 mm, another one is 0.75 mm. That means, so we have two different. So that means here this is what called as fine. Even this 0.5 pitch is more finer than this one. So like that we can define the coarse series and fine series. See now if you see here in M6, what is the pitch value here you have taken? In case of basic series, the pitch is 1. So here the starting one is going to be the basic series. Then if the pitch value is less than this basic series, then we'll call this as a coarse series. Similarly for M8, if you look at here for M8, the pitch value is 1.25. So therefore it is a coarse series, or we'll call it as a basic series. So now if you take the fine series here, M8 in cross 1.25 is the basic series. Then you have M8 cross 1 is going to be the fine series. So like that, you can designate the bolts based on its designation itself. You can identify that whether it is a coarse series or fine series. Okay. So then I think we are okay. So we already discussed this. I think this is what I want to discuss with respect to these fundamentals, or whatever we can call it as introduction to this bolted threads. So now we'll move on to the analysis part. So that means when a bolt is subjected to a given load. So here two types of loads will be there. One is initial load, what we call it as a load due to initial tightening. That means, so how the joint is formed. Let us say if I want to take a bolted joint, so through bolt is there. So I need to insert the bolt in the hole, then I need to take a nut and I need to tighten the nut. So now because of tightening, so you are tightening the nut. So before we are tightening the nut to form the joint itself. So therefore that's why due to tightening, there is some tensile stress in the bolt. So that tensile stress, what we call it as stress due to initial tightening. So to calculate the stress due to initial tightening, here from the bolt we know the area here directly. We know the area here from the data book or from the tables. You can take the tensile stress area. So you have a column, tensile stress area column is there. From that you can easily take that value. So now what is required is to calculate the stress value, or I want to calculate due to initial tightening what is the stress in the bolt. So to do that, I want to calculate, I need load and I need area to calculate the stress value. So area directly I am getting from the data tables. So then how I can get the load value? So I don't know how much you are tightening. So due to tightening, how you need to get the load. So that is again, there is some relation between load due to initial tightening, that is 2840 times D, where D is the nominal diameter. Again, this formula is available in the data book. I'll show it to you. So once you know the load, then you can calculate the stress value. So that is, you have a pre-stress. This one what we call it as a pre-stress condition. That means before applying the load to the joint, there is a stress in the bolt because the tightening of the joint. So that will call it as stress due to initial tightening or pre-stress. Stress due to initial tightening. So that is one kind of load. So then after that the joint is formed, the joint may be subjected to tensile load, or the joint may be subjected to the torsional load, or maybe the crushing load or some other thing like that, depending upon the load on which it is on the joint it is acting. You have different types of stresses are there. How we can calculate those stresses? Or sometimes you may have a combination of these things also. You have a initial tightening, you have external load. So then you have a combination or combined load. We call it as a combined load. So to find this, how you can use or where you will get the formula for that, how to compute the stress value, and then how you can compute the stress, and how you can design the bolt. So all these things. So today what I'll do is I'll take I think we have 15 minutes time left. So within that 15 minutes, I'll try to show whatever required for these problems. I'll show you how we can use the data book for that. So maybe in next class, if required, we'll take up those things in the whenever the topic comes. We'll discuss about the other things also. Okay. So now what I'll do is I'll come out of presentation mode so that I can show you the data book. If you have a data book now, then what you can do is you can open your data book also, no issue. Okay, so if you look at this table, okay, anyway, I'll come from the starting point. Okay, RS, okay, you can see that here. So we talked about how to compute the tensile stress area. So here, this table, I think it is page number 8.21. Threaded fastener is there in our data book. If you open this, I think it is visible to you or not? The table is visible to you?
Yes, sir.
Okay, so you can see that table 8.8 coarse and fine series threads. So you written the heading is something like this. So now in this you can see that just now we discussed about coarse and fine series threads. So here M25, the first one is yes, one it as M25 2.5. M2.5 is the What it means? M2.5 means a metric thread having a nominal diameter of 2.5. If you look at the last column here, so what is this last column? Tensile stress area in mm square. So for this M2.5, this is the tensile stress area. So for like that, for each and every diameter, he has given all the tensile stress areas. And in the bottom, if you come here in the bottom or in the bottom of the table, you can clearly see that how he calculated the tensile stress area formula also. You can see that 5 by 4 into d2 plus d1 by 2 whole square. So this is what we discussed, that is dp plus dc by 2 whole square. There dp is your pitch circle diameter and dc is the core diameter, what we discussed there. But here he has used a different notation. What he has taken? d2 plus d1 by 2. What is d2? Here you can see that in the table clearly mentioned that d2. What is d2? He has written here pitch circle diameter or pitch diameter. d2 is pitch diameter. And what is d1? So you can see that here d1 is your minor diameter or core diameter. Minor diameter or core diameter, we already discussed, they are same. So which is this one is denoted by dc and this is denoted by your dp as per our discussion what we discussed. But here he has used d1, d2 and d1. So the average of this d1 and d2 is taken here. So that's what we discussed in that while discussing about how we can calculate the tensile stress area. That is, the basic formula is only this. Based on this only, for each and every bolt he has calculated what is the tensile stress area. So that means if you open this table, not only this, you have another tables are also there for each and every table. If you have a tensile stress area. So here he has given only limited number of diameters. You can see the here M2.5 to M36 only there. Suppose if the bolt diameter is more than 36, the data is not available in this table. You have other tables. I'll show you that also. Those tables are also there. So up to 100 mm, their tables are there. So you can do only up to 36 mm here. So and also here I mentioned it as a coarse series and this is a fine series. So based on the pitch value, you can decide whether it is a coarse one or a fine one. So you can see that here the coarse series, the minimum. Okay, so the minimum diameter to use fine series is here. He has shown it as 8 mm. So below 8 mm, you don't have a fine series. Whereas in the table, what I have shown in the presentation, he has shown it as 6 mm is the basic diameter. So these things will vary from data book to data book. Don't bother about that. But here you have only 8 mm as the minimum diameter to go for fine series. So you can see that in case of fine series, you have different pitch values also. You can see that here. So once you decide here, sometimes in the problem, what they'll do is they'll ask you select a suitable bolt for this application, like that they'll give. So then, and sometimes they may ask you select a bolt with fine series also, like that also they may ask. If they don't ask about whether it is whether you have to select a coarse series or fine series, doesn't matter. Only you need to calculate only the diameter. That is nominal diameter of the bolt. Sometimes if they ask about whether you have to choose coarse series or fine series, then you need to use this particular table. Right? Okay, so this is one thing one table I want to show it to you. Then coming to the starting phase of this topic, that is chapter 8, that is threaded fasteners and power screws. Of course, power screws are not there in our syllabus. Maybe in our DMM 2 it is there. Here it is the power screws are not there. So in the data book, once you have a data book with you, the first thing what you need to do is at the beginning of the chapter he has given all the terminology. So that is important. You need to first go through the terminology. Then only you can understand whatever formulas inside the topic is there. You can understand them very easily. So for that, this is the important point. You need to, for every unit, you need to go through these designations. So for what capital D, for what he is using this capital D symbol, for small d, for what he is using, like that he has used different things, D1, D2, D3, like that. But in our discussion in the presentation, I have taken it as DP, D, DP and DC. But here he is using D1, D2, like that. So you need to be careful about the notations, because always we are not going to discuss the notation what we are discussed in the presentation. It may not be same here also. That's why already told you first you need to go through all these notations. So D, capital D is major diameter, small d is the capital D is the major diameter for the internal thread and small d is the major diameter for the external thread. That's what we discussed. So as for these two things, there is no issue. But the remaining things there are different. Are they are different. They in the data book the notation is different. So carefully go through all these notations. So accordingly you can substitute the data in the given problems. So now next, if I open to the next page, so in the next page, okay, anyway, this is not required for us. It is related to the turnbuckle, screw joints. Maybe sometimes you may get a problem on this also. If you get a problem on this, you can using these notations. You can whatever data he has given in the next pages. Using those data, you can easily solve the problems. So next, what I want to show it is yes, this page. Here you have some design particulars and equations. So like that you have a table here. So just now we discussed load due to initial tightening. You can see that here or initial tension due to tightening of the or tightening screwing. So for that we should know what is the load. So that you can take it here. P1 is equal to 2840D. What is D here? You can see clearly small d is used in the notation 2840 into D. So D is going to be the major diameter of the bolt. So why I said it is bolt? Because he has used the small d. Small d is used for the external threads. So generally external threads are on the bolt. So therefore we'll call it as a bolt. So in case of bolts, the initial tightening load is going to be Pi. It is denoted by Pi, which is 2840 times D, where D is the diameter of the or major diameter or nominal diameter of the bolt. Then P2 is externally applied load. So you have that means you use the two notations P1 and P2. P1 is load due to initial tightening and P2 is the external load. So then if you have two things, and a bolt is subjected to initial tightening as well as some external load, then to compute the resultant load, so you have that he has given in the first point, resultant load induced in the fluid tight joint. Resultant load induced in the fluid tight joint, which is given by, you have a formula PR, P suffix R equal to P1 plus, you have some formula A by 1 plus A into P2. You have a formula to compute the resultant load. So in this again you have a is unknown. What is A? All those things that he has given in the table form. Again I will show you that also. Here you can see that that is given as A by 1 plus A into P2. He has written it as P1 plus K into P2. Here K is given in the below of that formula itself. He has shown that he has written that for K values refer table 8.2. For K value refer table 8.2. That means if you go to the 8.2 table, you can easily see what are those values also. So I'll show you the table also. See, this is our table 8.2. This is table 8.2. The K value is different for the different types of joints here. So now he has listed 5 types of joints. So metal to metal joint with through bolts. If the joint is made between two metals and it is a through bolt, then the K value is going to be something like this. You can choose K is equal to 0 to 0.1. Any value in between 0 to 0.1 you can choose it. Similarly, you have a second type of joint, that is copper gasket with long through bolts. So that means first one is only metal to metal, means there is no gasket at all. If you use gasket, you have to use this formula. Then the next one is soft copper gasket. So again, depending upon the type of gasket you are using, whether it is a soft one or a hard one, you have again different K values here. So why it is? Because so the gasket while tightening it and while applying the load, the gasket will also take some load. How much load it is taking? So that based on that only you will get here your key values here. Similarly, packing material. So if you use soft packing material through boards, so what is the correction? What is the factor K? Similarly, the fifth one is soft packing with stud. If you use only stud, so like in case of screw jack, you have this kind of joint. So in that case, you need to take it as total load. Whatever may be the P2, you have to consider the entire P2 that is acting on the bolt itself. So that's why K is equal to 1 here. He has given it here. So like this, so first you can find the what is the initial load due to tightening. Then whatever external load is there, so you need to take that external load, but you are not consider the total external load because depending upon the type of joint, you need to choose the K value. Then if you multiply that K by given load, external load P2, so then if you sum up those two, you will get your resultant load. Once you get the resultant load, that resultant load divided by your tensile stress area. So I have shown that you again. Okay, one more thing, one more tables are also there. I'll show you that also here. Okay, so here you go to this table 8.7. So these are the tables which are corresponding to the metric threads. These are corresponding basic dimensions for design profiles of ISO metric screw threads. So he has given here. So you can see that here the first column is going to be your major diameter or basic diameter. Basic diameter is nothing but the major diameter. So it starts from 1. Again in that you have two pitch values. You can see that clearly. Two pitch values is there. First one is 1. The diameter is 1. But you have two different pitches values there. In that the first one is the basic series. The second one is going to be the fine series. A basic series in the sense it is a coarse series, and the second one is the fine series. Similarly, the diameter goes on increasing from 1 to 1.1, 1.2, and then you can flip the tables here. It is 1.4 like that. It goes on here 1.4 and 1.2 like that. It will goes on increasing those values. So for that. Like that up to how many things, so you may have how many pages. So next page it is up to 20. Here you can see 20 is there. Then similarly next page it is 36. 36. Then here in this page it is 52. Then the last one it is going to be 100. So we have data up to 100 mm nominal diameter. You can see that here 100. So here the nominal diameter he has given column 3. Column 3 is corresponding to the nominal diameter only. If you go to the first table, you can see it here. What is the column 3 here? Column 3 is major diameter. Column 3 is major diameter. Whatever number is here, this is same as this were major diameter or nominal diameter. So for each one, you have a last column as your tensile stress area. Here this one is your tensile stress area for each one. That means whatever diameter you have from 1 to 100 for all those bolts, you have a tensile stress area in the data book itself. So that means no need to calculate the tensile stress area. Only thing is you need to pick it from the data book and you need to answer it. Okay. So I think I want to show some more things. Maybe already it is 10:15 in the next class. So based on the requirement, where and when it is required, I'll show you those tables also and how we can use that those tables to solve the problems also. So for the time being, we'll stop at this point today. So we'll continue in the next class. I think I already placed the attendance sheet. Just respond to that attendance sheet and you can leave the class.